Welcome back, everybody. So we're going to get into chapter 7 now. You guys will find that, well, I guess in my opinion, I hope you find, that chapter 7 is, in my opinion, not as difficult as chapter 6 was, but it's just different, okay? And we're just going to learn a lot of new things in chapter 7. Okay? A lot of new things in chapter 7. Not necessarily more difficult things, just new things. Thank you. No problem. All right. Shout out, Aaron. Shout out. Hope you're watching at home. Shout out. Now, as we're going along, I do want to talk about one thing in terms of the videos. We're getting to the point of the year last year where I had started making my videos every single day, just like I'm doing this year. So I post it in the morning, like I've already published it in the morning, but I won't get around to actually posting this video, this particular one, and replacing the links, probably till around like 5th period, 6th period, sometime in there. So if you're at home and you're watching early on in the day, and you see, like, you hear voices that you don't normally hear, or you hear, like, or the video seems old or something like that, just check the date stamp. If it's a 2020, that means it was last year. So, think back, oh man, February 2020. How naive we were. What a year we were in, right? So it's just like a little flashback, right? It's not going to reach us, is it? Sorry. What was it? Oh yeah. So moral of the story is there. If you're clicking on the link at the beginning of the day, it's probably me from last year, unless it's maybe I was home or something earlier on. But anyway, the link should be live by 5th or 6th period. All right, chapter 7. Chapter 7 is all about exponential and logarithmic equations and logarithmic functions. Okay, you have no idea what a logarithm is yet, but I'll tell you, that's the kind of cool part about chapter 7 is we get to learn new stuff. Now let's talk about exponential growth and decay. Exponential functions and exponential growth and decay. The book likes to present this example where it talks about this thing called Moore's law. Anybody ever hear of Moore's law? It's like a computer law. I don't even know. The book presents this. Basically, it states that the number of transistors per integrated circuit, basically the processing power, doubles every year. I've heard this in a different capacity. I've heard this like technology seems to double every year. I don't know if that's still the case. But when I was growing up, technology was growing so fast and things were improving so quickly. It was seeming to double every year. I don't know if that's still the case. But like, especially early on when things were just kind of going nuts in the tech industry, things were doubling every year. But mathematically, let's think about that. Doubling every year. Do we have an equation that we've learned thus far this year to represent something doubling every year? Would it be just like 2x? Is that really doubling the value? Not really, right? It's not really just 2 times that value. It's doubling that value, right? Like, think about it. If I just took 2x and I plugged in 10, that'd be like 20, right? But if I wanted to keep doubling that value, okay, so 10, double it 20, double it 40, double it 80, double it 160, and so on and so forth. Okay, that's what I'm talking about. So it's not really necessarily just 2x. Like, think about the table here. We're doubling every time. Remember back in linear functions where we were able to see a constant set of differences within the y values? And then we talked about quadratics, and we talked about the second differences, we talked about cubics, we talked about the third differences. And we can keep that going. When we look at something that could be what's called exponential, we see something doubling every year. Like, take, for example, this. What if I offered you money? What if I had said to you, okay, I'm going to give you $1,000 a month. That's option A. $1,000 a month for a year. How much are you going to have at the end of the year? $1,200, right? So what if I had said I'm going to give you $1,000 a month each year? Or, sorry, 1 month for a year. Or I would give you $10 and double the amount of money you had for a year. Which option do you think you should take? Which option do you think you could? I mean, honestly, that $1,000 a month is pretty enticing, right? You're like, ooh, okay. However, if you took $10, if you took the $10 option, think about it. Okay, so I gave you $10 on January 1st. On February 1st, I doubled it. March, April, May, June, July, August, September, October, November, December, and then let's say we did it on January 1st. Holy chicken nuggets, man. What would have been the better deal? Taking the doubling every month, right? So, and notice early on, it wasn't growing very quickly, right? Like February 1st, I'm only at $20, right? And then March 1st, I'm only at 40. And then by April, I'm still only at 80. And then 160. You'd be thinking at that point, man, I've got thousands of dollars in my bank. Why did I ever choose this $10 doubling every month option? But by the end of it, you're going to have a lot more. See, we're going to see here that exponential things grow rather quickly as time moves on. Okay? It doesn't grow at a constant rate. It actually grows at a curved rate. It's this thing called an exponential. Okay? Growth that doubles every year can be modeled by, or doubled every month, can be modeled by using a function with a variable in an exponent. This function is known as an exponential function. So the key here is having the variable within the exponent. Okay, we haven't had this yet. The variable has to be within the exponent. The x is up in the exponent. So f of x is equal to b to the x, where b is our base. Okay, b is the base, the thing being raised to the exponent, b to the x. Okay, that's our generic form of an exponential function. Y is equal to, or f of x is equal to b to the x. And now I say f of x right away because I'm implying to you that these are always going to be functions, which is true. These are always going to be functions unless I do something really funky to the equation. But if I call it an exponential, that's really just, it's always going to be a function. Now, so this is our generic form again. F of x is equal to b to the x, where b is greater than 0 and b is not equal to 1. Let's talk about what would happen if b was negative. What would happen if b was negative? Because I make this stipulation where b has to be greater than 0. Yeah, it would, because what happens when we have a negative? You gotta add the sound effect. But because what would happen if I take, -2 raised to the second power? It'd be a positive number, right? So what happens if I take -2 raised to the third power? Negative. What happens if it's to the fourth power? Positive. Negative. Positive. Negative. Positive. So it jumps around a lot. So it's no longer exponential. It doesn't have that exponential form. Also, b cannot be equal to 1. Why is b not equal to 1? What happens when I take 1 to the x power? It's always what? 1. 1 to the 5th. 1. 1 to the 10th. 1. 1 to the millionth. 1. It doesn't matter. So that actually comes out to be a constant function. Okay? That actually comes out to be constant. So what are we implying here? What's left over? Well, b could be somewhere between 0 and 1, not equal to 0, not equal to 1. Or it could be anything bigger than 1, right? And that's going to define whether we have exponential growth or exponential decay. Now, our parent function, we study parent functions a lot. Our parent function of an exponential is going to be 2 to the x. That's our most basic exponential function. Because we got to put some base in. We got to put a numerical base in. Can't put 1 in because we just talked about that. It'd be constant. So let's pick the next whole number, 2. So y equals, or f of x is equal to 2 to the x. Think about it. What happens if I have negative exponents? Is it going to turn out to be a negative number? No. It's going to turn out to be a fraction. 2 to the negative second power, that's 1/4. 2 to the negative first power, that's 1/2. 2 to the 0 power, what's that? 1. So any any basic exponential function is going to have that 0, 1. So here's how this looks. What would happen if I continued that negative on out? What would be 2 to the negative third power? Like I know you're filling in your table right now of negative second, negative first, 0, 1, 2, 3. Right. But what would happen if I extended that into more of the negative direction? 1/8, 1/16, 1/32, 1/64, 1/128. Would I ever get to 0? Is there anything that would actually get me to 0? No, I could go infinitely into the negative direction, and it will never actually reach 0. This is the first time we've seen something like this. This is called an asymptote. Okay, this is called an asymptote. The idea of an asymptote is if I continue that pattern infinitely, it will get very, very, very close to that thing, but never actually reach that thing. Okay, that's the idea of an asymptote. It's going to get very, very close to, but never actually reach it. It's going to get very, very close to the x-axis, but never actually intersect the x-axis. It doesn't have an x-axis. Okay, that's the idea of what an asymptote is. All right, so let's talk about domain and range. The domain is always going to be all real numbers because I can plug anything in left and right. It's going to continue on forever left and right. I could plug any number I wanted to up into that exponent and evaluate it. But the range is what's going to be different. The range here, because it's going to have that asymptote at x equals 0, or excuse me, at y equals 0, I'm going to have to say, well, the range, therefore, is then all numbers greater than 0. So that's written out in set builder notation. If you wanted to write it out in interval notation, you would say 0 to infinity. Right, 0 to infinity, not including 0, because again, it's never going to actually reach 0. The y value is never actually going to come to be 0. And remember, you never include infinity. So the domain is always going to be all real numbers, and the range is going to be all numbers greater than 0. So 0 to infinity. And I already talked about it already, but the next part here talks about the idea of an asymptote. Notice that as the x values decrease, the graph of the function gets closer and closer to the x-axis. We could actually even write it like this if we wanted to. We could say as x goes to negative infinity. Think about this. Doesn't this look really like end behavior-y, right? Like what we talked about on the last chapter test. We say as x goes to negative infinity, as I get smaller and smaller and smaller with my x values, what happens to my function? Does f of x go to positive or negative infinity? Does it go forever up or forever down? No, it goes to 0. F of x goes to 0. And that's how we can write that. That's a formal way to write that. In calculus, you'll learn to use the limits. You'll say the limit as x goes to negative infinity equals 0. That's another way to write that. Okay, the function never actually reaches the x-axis because the value of 2 to the x cannot be 0. Think about that algebraically. If I had 2 to the x is equal to 0, we don't know of any number x right now we could use to plug that in. Actually, we don't even know how to evaluate when there's an x in the exponent, right? We don't know how to algebraically do that yet. Spoiler alert, it's a logarithm, which we'll learn later on. But again, in this case, the x-axis is what's called an asymptote. An asymptote is a line that a graph function approaches as the value of x gets very large or very small. A lot of the times in our class here, we're going to learn about asymptotes that are either horizontal or vertical. Okay, we're going to have horizontal asymptotes, and we're going to have vertical asymptotes. By the time you get to pre-calculus, you're going to learn how to evaluate slant asymptotes when the lines are slanted, but they're still it still acts like an asymptote. Okay, again, an asymptote is a line that a graph function approaches as the value of x gets very large or very small. The function of the form a times b to the x is called either exponential growth or exponential decay. Exponential growth is when that b value is going to be greater than 1. Okay, greater than 1. If b value is greater than 1, it's exponential growth. Okay, if the b value is greater than 1, it's exponential growth. If the value of b is between 0 and 1, that's when it's exponential decay. See, remember back when I said, okay, what was left over? Well, the b values that were left over would be anything between 0 and 1, which would mean exponential decay. And then anything bigger than 1, which would mean exponential growth. Obviously, the words growth and decay tell you exactly what's going to happen within the function. As my x values get bigger and bigger in terms of a growth, the y values are going to get bigger and bigger. In terms of decay, as my x values get bigger and bigger, my y values are going to get smaller and smaller. Right? So let's take a look, tell whether the functions represent a growth or decay, and then we're going to graph it to kind of verify and see whether it actually represents growth or decay. Now, I'll tell you this right now, the 10 says nothing about whether it's growth or decay. You know what the 10 is actually telling me? That the starting value is 10. Whatever I'm evaluating here, whatever I'm observing here, the starting value is 10. And we're going to see what happens as I take a 3/4 to the x applied to it. All right, so what does this tell me? Is that going to be growth or decay? Decay. It's going to be decay. And we know because it's less than 1. Obviously, it's bigger than 0. It's always going to be bigger than 0. It's between 0 and 1. Okay, so let's take a look at it on our graphing calculators. Okay? All right, I'm going to go into my y equals, and I'm going to plug in 10 quantity 3/4 to the x. 10 quantity 3/4 to the x. I don't know where my calculator's been, so I'm going to hit zoom 6. Remember, zoom standard gets you back to your normal 10 by 10 window. All right. So this is what exponential decay actually looks like. You know, I could continue this graph on if I'd like to. You know, up there, it will continue forever up here and then down here. Now, I'm going to need you to be very careful when you're drawing your graphs by hand. I'm going to need you to be very careful. Should that blue line ever intersect the axis? No, because that's the idea of an asymptote. And I'm going to be very picky about that. If you get sloppy and make your line look like it goes through the axis, I will take points off. 100% I will take points off. Because if you make it go through, I know that you don't technically understand the idea of an asymptote. Okay? It's going to get closer and closer and closer to that x-axis, but never actually reach or go through that x-axis. So this is what an exponential decay is going to look like. As my x values increase, my y values get smaller and smaller and smaller. It converges to 0.
Are there two lines parallel down the middle? Like if you cut that line in half, is it parallel or not?
Which one? This?
Yeah, like draw a diagonal line right down the middle. That. And then is that parallel?
To what?
Like is each side of it parallel?
Oh, you mean like congruent, like symmetrical?
Yeah.
No.
No. Yeah, that's what I want. Symmetrical.
Yeah, it's not necessarily, it almost looks like it would be, but it's not necessarily symmetrical. The line would have to be a little bit more slanted upward. Yeah. It's not technically almost like a parabola on that side. Yeah. All right, take a look here. That 100 in front of the parentheses tells me nothing about whether it's going to be growth or decay. The 1.05 tells me it's going to be what? Growth. Because it's bigger than 1, I know that this is going to be growth. That 100 is actually telling me that I'm starting at 100. That's the starting value of whatever I'm observing. All right, y is equal to, I'm going to change this to 100 times 1.05 raised to the x power. So I say that this should be growth, so it should look like it's going upward instead of downward. I'm going to zoom 6 and see what happens. Now, I don't see anything. Why don't I see anything? Because the starting value is 100, right? If I plugged in 0 in for x, what's my y-intercept? 100, right? 1.05 to the 0 power is 1. 100 times 1 is 100. So let me do this. Let's manipulate our window a little bit. Let's go zoom fit. Why not? Usually that works. Let's see zoom fit. Yeah, I mean, I guess we can see it here as much as we really need to. And here's my axis is probably down here somewhere. But here's my line. Now, what do we notice here? That in relation to what we saw before on the decay, the growth is not actually as fast as the decay was on the last problem. We're going to see that the closer you get toward one, the shallower that growth, okay? The closer you get toward one in terms of your base, the less amount of growth or decay that you actually have. Like if you get closer and closer to one from the low end, like 0.9, 0.99, 0.999, that's still decay, but it's just a really shallow decay. The closer you get toward one from the high end, 1.05, 1.04, 1.03, 1.02, 1.01, the shallower it gets. But it's still growth, but it's still, it's just a little bit flatter of a line. Okay. Now, let's talk about it in real-world problems here. You can model growth or decay by a constant percent increase or decrease with the following formula. And this is something that you're going to need to memorize. Make sure you have this committed to your memories here. All right. This is the standard form for exponential growth or decay. Okay, this is our generic form for exponential growth or decay. What we have on the outside of our parentheses is our initial amount, kind of like what I've been alluding to earlier on. That A value, that lowercase a, is our initial amount, the starting value. You're going to observe population. The population is at 2 million people. Your 2 million is your A value. Now, that 1 plus or minus R, that R is your rate of increase. Or it could be your rate of decrease. And that's what would change from the plus to the minus. Obviously, if you're going to increase in any amount of rate, that's going to be above 1. So it's going to be exponential growth. If you're going to decrease in any sort of rate, that means that's going to be 1 minus a certain value. That's going to be a certain decay. Okay, so if I'm increasing it, 95% increase, my 0.95, notice I turned it into a decimal, my 0.95 would be my 1 plus 0.95, 95% increase. But what if I was saying like a 20% decrease? Well, then that would be a 1 minus 0.2, right? Because I'm decreasing in that value. I want my base to turn into a number less than 1 because it's got to be a decay. And then T is the number of time periods that you're going to look at. So say I wanted to look at it in terms of like 3 years. Well, then T is my 3. Okay. Let's take a look here. Yeah, obviously the 1 plus R, the 1 minus R, the growth. Sometimes you might see that called the growth factor or decay factor, like identify what the growth factor or decay factor is. Basically, I'm just asking you to identify what the base of the exponent is. Okay. Yeah, let's do an example here. Clara invests Clara. Let's make this a little bit. Let's say Sadie. Let's Sadie in. Yeah. Anybody know anybody named Clara? You do?
My cousin.
Oh,
I
sorry.
don't know anyone named Sadie either.
Now you do. Okay.
Clara?
Clara. All right. Clara. I'm like, what's his name? What's that Christmas movie where he wishes he was never born? It's a Wonderful Life. Clara. What are you doing, Clara? Sadie invests $5,000 into an account that pays 6.25% interest per year. After how many years will investment be worth $10,000? All right. So this is exponential growth or decay? What do we think? Growth or decay? I would hope it would be growth. She's paying out 6.25% of her money each year. I mean, getting paid out 6.25% of her money each year. So what's my initial starting value? What's my lowercase a value? 5,000. Times 1 plus, because this is growth. The growth is telling me that this is going to be a plus. And then my rate as a decimal, 0.0625. Please don't say 0.625. That would be a rate of 62.5%. Please find a bank account with 62.5%, please. 6.25% interest is 0.0625. And it says, after how many years will investment be worth $10,000? So I don't know the number of years. The x is my exponent. But I want to know when this is going to be equivalent to $10,000. Now, pause for a moment here. Don't do any work with me. I just want to show you something here. Like, okay, obviously we could reduce this down. I'm going to put it in blue because I'm going to erase it in a second. Because I really just want to solve for x, right? That's the goal here. I know we're going to go to our graphing calculators and do this, but what if I had just, combined the piece inside here and said 1.0625 to the x is equal to 10,000 divided by the 5,000, 1.0625 to the x is equal to 2. And then what would be my next step to solving this algebraically? Would I square root? I would only square root something if there was a 2 up here, right? Like that's how you undo a square. If this was like an x squared, then I would square root the opposite side. So it's not necessarily square rooting. Actually, we don't know how to do this yet. You don't know how to solve that yet. That's an unknown. We actually will use what's called a logarithm. But what we can do is put it into our calculators. So let's do that. Let's go into our y equals and say, okay, I've got $5,000 in my account, growing at a rate of 6.25%, so 1.0625. Yeah, you could write in the full 1 plus 0.0625 if you wanted to. Raised to the x power. And then I'm going to say, okay, my second y value is going to be 10,000. 10,000. I'm going to zoom 6. But obviously, am I going to see anything here? My starting value is 5,000. So let's zoom fit and see what happens. Hopefully I see a curve and then a horizontal line running along the top. Okay. Come on, intersect on the screen. Oh, that's a big bummer. Oh, it's so close. It's so close. I got to zoom out. Zoom 3, enter. Let's see. Dun, 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 dun. Okay, let's find out where they intersect now. Second, calculate intersect. Remember, it's first curve, enter. Second curve, enter. Yes, enter. Okay, how long is it going to take for her investment to get up to $10,000? 11.43 years. And we'll just leave it as a decimal. 11.43 years. Earlier on when I had said I'm going to be doubling your money each month, you know what percent interest that was? 100% interest. Right? That's what that was. 100%. I'm taking all your money and I'm doubling it. That's 100% interest. That's why it was 2 to the x power. So 11.43 years. That's how long it would take. Let's do one more of those. A city population which was initially 15,500 has been dropping 3% a year. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000. And what will the population be in 10 years? Okay, let's start by creating our equation. All right, my initial amount is 15,500. I know that this is going to be dropping, so it's got to be 1 minus 0.03 to the x power. Please don't say 1 minus 0.3 or 1 minus 3. That would even be worse because that would turn out to be a negative base. So just to reduce that a little bit, we could just say 15,500 times 0.97 to the x. And right now we see that is indeed decay because it's less than 1. 1 minus 0.03 is 0.97. All right, I want to know when that's going to be 8,000. When is it going to drop below 8,000? So I go to my y equals. I'm going to clear out everything that's there and write 15,500 times 0.97 to the x power. And I'm going to go down in here to my y2 and say, okay, I want to know when the y value, when this output is going to be 8,000. 8,000. I'm going to zoom fit this and see what happens. I see my decay. Let's see if there's an intersection point coming along the bottom here. Oh, sweet. I didn't even have to zoom out or anything like that. That's fancy. Second, calculate the intersection point. Hit enter 3 times. Wait for it to come up. It's going to take 21.71 years. 21.71 years to get to 8,000. It then says, okay, well, how long, or what will it be in 10 years then? It's going to take 21 years to go below 8,000. What's it going to be in 10 years? Well, isn't 10 an x value? I could have gone to my calculator and just plugged in 10. But since I'm already here on my graph, second, calculate the value at 10. 10 years, it's going to be 11,430 people around. 11,430 people in 10 years. We're going to find that exponential growth and exponential decay happen a lot in real life. A lot in real life. Actually, exponential functions occur a lot more than polynomial and linear and quadratic and whatnot. Okay. All right. Sorry, I got you 12 minutes. That sound good? More than nothing, right? So long, everybody at home.